Hi, we were examining chapter 2 Boolean algebra. The first frame is related Boolean algebra. Axiomatic structure of Boolean algebra has been explained here. Now we will be explaining this second frame here, which says Boolean functions. Boolean functions. For Boolean functions, we've got two videos. One of them is related the Shannon theorem, which is a theorem, critical theorem to understand the logic circuits. We are going to define these Boolean functions. Why we are spending so much time on Boolean function? Because each combination circuit, a circuit which is combined by the gates, can be represented just by one Boolean function. Therefore, the Boolean functions are important for us. So let's go in the open board, escape here, go to the open board, and the open board. I've got to switch the open board, therefore I need some time to do that. So okay, that is the open board. We will see it now. Here you are. So this is, let's start with the n variable Boolean function. That's the definition, of course. By applying plus multiplication and complement operations to the x1, x2, xn variables, each function defined s to the power n to s is called Boolean function. Another way of saying it, any function that you defined between s to the power n to s is a Boolean function if you can write it as a formula. For example, if you ask me, find a Boolean function, for a three-variable Boolean function, I can easily write it like that. F x1, x2, x3 is equal, for example, x2, x3 prime plus x1, x2 multiplied with x2 prime plus x1. This is a formula. How I found that formula? By using these operations on these three variables. This is what I've done. So I am saying now, if you can write a formula like that, I know that this is a Boolean function. What does this mean? Is this: if a function cannot be written as a formula like that, then it is not a Boolean function. So why we need that? Because when we are modeling the physical world, let's say logic circuits, while we are modeling it, we are going to use the mathematics. This model must be a formula form model, is easy to deal with. Otherwise, if you don't have that formula, so you're going to use tables, isn't it? So truth table, what we call it, x1, x2, x3. In this list here, if you've got s on which the Boolean function that we are dealing with defined, that is s. This cardinality of this cell, if it is n, example, let's say n equal to 4, so the s is going to have inside 0, 1, a, b. 0 and 1 must definitely be in, because in the axioms we've got the definition of that 0 and 1. So if it is like that, if you define a Boolean function from s to the power 3 to s, it's going to be a table like that. That's their function. So zeros and goes like that, all ones, and you're going to get function values for this, isn't it? Let's say 1 here. And the others are going to be the one which includes A and B in it. For example, 0, 0, A. The last one may be B, B, B. So the number of elements in here, if it is, if the number of rows here is equal to the power n. Why is that in general? Why is that? You're making a permutation which is combined of n tuples, isn't it? So the number of permutations that you can write is 2 to the power n. But if it includes all the elements of S, then it's going to be this one. So the number of rows here is going to be 10 to n to the power small n. Why is that? Because we've got 4 symbols, we are making n tuples out of these symbols. So this is the total number of symbols that we're going to have. So the conclusion, so a function is going to be something like that. Now what we are saying, this is a big table, isn't it? In order to represent one function. Instead of this, for the Boolean functions, we have a chance to write a one line here, represent the whole table here. So it is simpler. That's why we are preferring formula written type of functions, which are called Boolean functions. Now let's come to the theorem. Theorem tells us any Boolean function, n variable Boolean function like that, can be written in this form. What is this form? You are taking one of the variable, maybe in here xi, out of the function. How are you going to, here you are, xi prime and xi. And the coefficient of xi prime, make it a different color, this coefficient. There's a coefficient here, coefficient of xi prime. If this is the original function, in the original function, if you replace xi variable with 0, that is xi equal to 0, when you replace it in the function, you're going to get n minus 1 variable function, isn't it? Because if you put that xi equal to 0, wherever you see that xi, it is going to disappear. If it is a summation next to it, 0 plus something gives you whatever you summed with. If it is 0, whatever terms that you multiplied with, that term disappears. So if you have got an variable function, if this is a Boolean function, if you replace one of the element value, one of the variable value with 0, you're going to get n minus 1 variable function. This function is also going to become going to be a Boolean function, because in the formula you are replacing one of the variable with 0, so you end up with another formula. So this new formula, n minus 1 variable formula, this is a new Boolean function. Number of variable, this one is n variable and this one is n minus 1 variable. Similarly, the second term has got a 1 coefficient as well here. This is the second term coefficient. Not second term, I should have said variable itself multiplied with a coefficient. In here, variable prime is multiplied with a coefficient. Variable itself multiplied with a coefficient. This coefficient, how I'm getting that coefficient is this. You're going to replace wherever you see in the formula of this function xi, you're going to replace it with 1. So that means this variable is going to disappear once again in this form. We are going to end up with another n minus 1 variable Boolean function. It became a bit long to explain that, but it is simple. What we are doing is this. We've got an n variable function. We are taking out one of the variable of this function, which is this xi, and putting in front of this xi variable, in front of it, a coefficient. This coefficient is constructed from the original function by replacing the variable x0 for finding the coefficient of xi prime. Similarly, xi itself coefficient. In order to find that coefficient, you're going to replace the xi value in your function with 1 and end up with n minus 1 variable function. So any Boolean function can be written in this form. So if we consider, if this is going to be, this is a theorem, this is going to be proved, but we are not going to give you this proof here in this course. It takes a bit long time. In my Turkish course notes, there is a proof of it. You don't need any language to understand that. It is mathematics. So you can follow that up, or you can see the proof of this theorem in different logic design books. So we are saying the next step is dual of this must be, since this is a theorem, dual of this theorem should also be true. How are we going to find the dual of a theorem? Is just remind you what duality principle was. Wherever you see plus, you're going to replace it with multiplication. Wherever you see multiplication, you're going to replace it with the sum operation. Wherever you see 1, you're going to replace it with 0. Wherever you see 0, you're going to replace it with 1. So if we apply this duality principle to that formula, we're going to end up with, so in here, 0, you're going to be replace it with x equal to 1. And then there is a multiplication in here. So between this coefficient and this, there is a multiplication here. For this multiplication, we put here plus. And there is a plus here. We put the multiplication in here. Wherever you see plus, put the multiplication here. And this xi equal to 1, replace it with 1, replace with 0. And there is a multiplication here. It has been replaced with that plus here. And what we end up with, this is a product term. This is another product term. You are summed them up. In here you got a one sum term. This is the second sum term, multiplication of those two sum terms. Now, without proving we accept that this theorem is true, what we can think of next is this. Can we apply the same theorem to this coefficient function now? We said the coefficient function is n variable 1, n minus 1 variable function, Boolean function we said. So this theorem says all Boolean functions can be written by taking one of the variable out, can be written in this form. So next step is this. Can I apply Shannon theorem to this coefficient and to this coefficient as well? This time by taking xj variable out. So let's do this now. This is black one. So in here we've got here f x1 point xi xn xi is equal to 0. This is the coefficient. So this is the n variable, n minus 1 variable function. So if I apply this function, same Shannon theorem once more, for this time for xj variable. So it's going to be now f x1 point xi xj point xn. While xi equal to 0, I am going to put xj this time equal to 0. So xj prime is going to come in. So this is the original function. So we wrote the same as this. And then now we are saying in this n-1 variable, I am going to replace xj variable this time with 0, multiply it with xj prime. So the second term is going to be this original function, write it again, xn, xi equal to 0. That is this function. In this function, if I replace xj with 1, it's going to multiply it xj itself. In here, xj prime, in here, xj. What I have done here, this n variable, n-1 variable Boolean function has been written according to the Shannon theorem for xj variable. So if you do the same thing for the second coefficient here, make it different color. So in this second we've got x1, xn, xi equal, this time 1. Expansion of this function, n-1 variable function. So I'm going to read this once again. x1 xn, xi equals 1. This time xj, I'm going to replace xj variable in this function with 0, and my variable is going to be xj prime, since put 0 for this variable. So the second term is going to be x1 xn, xi equal to 1, xj equal to 1, multiplied with xj. So what I have done in that blue one here is this function. So this one, the black one, is this function. Apply the Shannon theorem for the variable xj prime, xj prime, xj. Now we are saying, what is the original function if I consider xi out, xji out? Why we are doing so? Because we are considering the first step, Shannon theorem takes one of the variable out. So if I apply the same theorem for each variable, so x1 out, x2 out, xg out, xn out, so you're going to take all the variables out. What is going to left is going to some coefficient multiplied with product terms. So you could see it here now. So I'll show you now, if you write this original function here, after we did the operation to this black and blue coefficients. So the black one is going to be multiplied xi prime. Let me show it in different color. So this is xi prime is going to be multiplied with this. So that's going to be xi prime. This is j. This is xi prime is going to come in. So the second one is going to be multiplied with xi itself, not the prime, but itself, xi itself. So that's going to be multiplied with xi, and that's going to be multiplied with xi. That one is xj, and this red one is xi. What we are seeing here, we've got two terms. Now it became four terms, but this time we've got four variables, four product terms we've got. Four terms we've got. Two instead of two. I've got four terms and two coefficients out, isn't it? Two variables out, xi and xj. Out, four terms. If three variables you take out, it's going to be 2 to the power 3, 8 terms summed up. If you continue like that, at the end you're going to end up with an expansion like that. If you look at this expansion, you got a coefficient here. In this coefficient, if the variables are replaced with zeros, the variables primes or complements are going to be seen as the product to this coefficient, right? So the next one has got 0 and this coefficient, all of them has got 0s and 1s only. In the second term here, if you consider this in decimal 1, in binary 0, 0, 1, the first n variables, since they have got 0 values in the coefficient, these variables primes are going to come in. If the variable value is 1, so this variable itself is going to be the same as the product term. So if we continue like that, the last to the power n and coefficient here is going to have these all ones in it. So that means this, you see. And the product term here is going to be, wherever, since the variable is replaced with 1, the variable itself is going to seen here, as it is here. xi1, the variable itself comes out. So I can make it, maybe it seems a bit confusing, but I can make it simple for you. What I have got here for this 3 variable function is the coefficient, the function value for this coefficient, isn't it? So that is here, is this. And it goes like that. The second one is 0, 0, 1. The last one, all ones, here is the function value, let's say this. It could be any a and b or 0 and 1. This is this term, this coefficient here. So that means if I've got a table like that, and this table represents a function, if this function is a Boolean function, this special 2 to the power n number of points function values known, if I know these function values, then I can write this Boolean function in this form. That's the conclusion. So if you look at this formula now, this is going to be any value, and this is a product term because the variables are multiplied here, so it is called a product term. These product terms, these ones, are called min terms. And if you consider the dual of these terms, you're going to end up with this. You could easily find out this. So anywhere you see zeros, you're going to replace it 1. This happens in here, isn't it? That is the dual of this. And this last one here is the dual of this. So if you get the dual of it, instead of product terms that you see here, they're going to become sum terms. So sum terms are multiplied here. Product terms are summed here. So this is called sum of products. This is called product of sums. There is another name for those. This is also called first type canonical form. That is the second type canonical form. So this is, so how many terms that we've got here is to the power n, because this special to the power n values is enough for us to write the Boolean function. You see, in the theorem we said this can be done only for Boolean functions. This there are some hints that we can get out of this. Is this? So if you know this special definition set terms, why it is special, so they include only zeros and ones, not a and b's. For these special coefficients, if you know the function values, then by using this formula you can find these functions, the other definition set elements, what the function value is going to be can be calculated by this formula. This Shannon theorem tells us this. So if you know this part of it, if it is Boolean function, you can find this part. You don't have to put those in. You can calculate it by this formula. So the solution that we are going to get out of this is this. So the number of functions that you can define between these to the power from s to the n and to s, the number of functions you can define between two sets is n and small n. Why is that? You see, you've got n to the power n number of rows here, and you've got n number of symbols. So by using these symbols, you're going to write a permutation. Each permutation represents a function. So these are the total number of functions that you can represent between those two. Now we are saying if you know the special to the power n number of rows Boolean functions values, so Boolean functions for the other values, you cannot use any permutation you like. You're going to calculate these coefficients, these function values, according to this formula. So you can only choose this part as different permutation. Each different permutation represent a Boolean function. Pay attention, I said Boolean function. So the number of Boolean functions is the number of permutations that you can write with these two symbols, zeros and ones. So n to the power 2 to the power n is the number of Boolean functions that you can write. If you subtract this, you can find non-Boolean functions. Now, very interesting conclusion that we are going to end up with. If capital N is equal to, so this is 2 to the power small n minus 2 to the power small n equals to 0. That means if S set has got zeros and ones in it, not like this, then all the functions that you can define between s to the power n to s, they are all Boolean. Means they all can be written as a formula like that. How are you going to write that formula is this Shannon theorem, right? So this is mathematical conclusion. Now let's come to physical world. In physical world, we have digital systems. In digital systems, we said we've got the signals which has two values, zeros and ones only. So in the physical world, we've got zeros and ones. That means the set A has got zeros and ones in it. Then all the functions are Boolean. So that's good news for us. If S set is this as it is in the physical world, then any n variable functions can be written as a formula. So that means non-Boolean functions we are not going to face with. Good news. So we can write all the functions as a formula and do the operations on those formula much easier. Do the operations on tables like that, because these tables are big tables. Now, the one thing here, you can say that, okay, it seems that it's not a big table, it is a small table, but even the small table, if the number of variables increases, so the number of rows that you're written here is to the power n, isn't it? If n is high, so it's going to be a long formula that you're going to have. So the next explanation is related with this. We can write this formula in this form, just one line. How we are going to write it? You see in here, sum of products. So this is a product term, summation of the product terms. So what you see here, each term is a product term, the summation of the products. So summation of the products. In here, we've got this coefficient and this term. We represent this coefficient as this, if I value is equal to 0. So as I said in the previous one, we've got here 2 to the power n rows. So that means to right of each rows, my I goes from 0 to 2 to the power n minus 0. That means if you start with 0, this is the first row, second row goes at the end 2 to the power n minus 1 you end up with. If you start the counting from starting from 0, so the total number of 2 to the power n rows, but in decimal numerical case, if you start from 0, 0 to 2 to the power n minus 1. So that's why we see that I equal to 0 up to 2 to the power n minus 1. So I is a decimal. Consider the I as a decimal and transfer it to a binary. So this representing a decimal number here, I, in binary. So this is a long representation. This is a short representation. This is binary. This is decimal. So this one, for example, in decimal 1, in binary it is zeros and the last one is 1. So if you go up like that, 2 to the power n minus 1 is this one, this decimal number. If you represented it in binary, it's going to be all ones. So now I's coefficients are these coefficients here. Now this is the coefficient. Now let's come to this product term here. This product term is f equal to 0 for this one, for this coefficient. What is going to come next to it is m0. When this is 0, you're going to write that 0 in binary. That means these variables are going to be zeros. So if it is 0, function value is 0. That means this. Then the corresponding variables are going to be in the complement form. So x1 prime, x2 prime, x3 prime, the previous rule that we already said. So when you come to the final one of it, m as an index 2 to the power n minus 1, representation, binary representation, these all ones. So according to the rule that we already said, if one variable is replaced with 1, the corresponding variable is going to be itself, not the complement of it. So these are the product terms that we are talking about. These product terms are called min terms. This is the coefficient of the min term. Now let's consider now if the function value, these are the function values, if the function value is equal to 0. So if the function value is equal to 0, 0 times that min term. 0 multiplied something gives you 0, isn't it? So if the function value for a min term is equal to 0, then this term disappears. We give a special name for this term. This term is called false min term. If the function value is equal to 0, this coefficient related min term is called false min term. If the function value is 1, then the corresponding min term's name become true min term. Conclusion from that is this. How are you going to write a function in this form? It's easy. You're going to say it, write summation of true min terms. Because false min terms are going to disappear. So if you got numbers of one values in your Boolean function, then you can write this Boolean function as the p number of true min-term summation. Similarly, this is the dual of this. So you see here, this sum term becomes multiplication term, and this is there is a multiplication here. This becomes a summation here, isn't it? So this multiplication here is summation. So you're going to end up with this. This is the second canonical expansion. The coefficients are the same, but these terms are different. This is a small m, this is a capital M. The difference is these are the product terms, these are the sum terms. How we are writing the sum terms, if the coefficient is this, so this is capital M0, so this variable values are going to be 0 in binary. So as we said already, in the second canonical form, if one of the variables replaced with 0, then this variable itself is going to be the same in the sum term. So 0 variable itself, 0 variable itself. So these terms are called max terms. This is the coefficient. So if you continue like that, the last max term, so capital M to the power n minus 1 means in binary 1, 1, 1, like that. So the corresponding sum term variables is going to be complement form, since the variable is replaced with 1 here. Okay. So the conclusion that we can get out of this, if the coefficient is 1, this max term disappears. 1 plus something gives 1. 1 multiplied anything gives you whatever it is multiplied with. So if the coefficient is 1, this term disappears, and this term has a special name. It is called false max term. If the coefficient is 1, this is written here min term, should have been max term, false max term. That means disappeared max term, because the coefficient is 1. That is not going to be the same in this expansion. If it is 0, that means if the coefficient is 0, which is the opposite what we said here, if the coefficient is 0, this term is going to be seen. So this max term is going to be seen, and this max term has a special name. It is called true max term. Conclusion is this: if you are writing a Boolean function in second expansion form, you're going to multiply the true max terms if you do the multiplication of it. So that is the formula that you required, or the second expansion. So conclusion is multiplication of the true max terms. So that's end of this video then.